My name is Elifari. I would like to demonstrate the solution of example 3.8. At the same time, I will explain how we can use the textbook to solve the problems. As you can see, these problems in the textbook are in US units, and we have the metric unit here. Okay. Here we have a crank which is loaded with by force equal to 1.3 kilonewton. That causes twisting and bending of 20 millimeter shaft. That means this shaft AB, which is fixed to a support at the origin of the reference system. That means here. The support may be in an inertia that we wish to rotate, but for the purpose of stress analysis, we can consider this a static problem. So that means we will consider the system is fixed and maximum stress will be uh, imposed to the system. In part A, we are required to draw a separate free body diagram of shaft AB and arm BC, then compute the values of all forces, moments, and torques that act on the system. Then we need to label the direction of the coordinate axis on this diagram. If you refer to the textbook, you can see that the free body diagram of each shaft has been drawn and the direction are determined. Later on, the load uh, equation has been written in this way. But I won't solve the problem in this way because this way is quite time consuming and confusing. So I try to solve in a simpler way. Okay. If I draw the problem here, first I would like to analyze the arm BC. Analyze the arm BC. Okay. At the continuous of this problem, in part B, we are required to compute the maximum of the torsional stress and the bending stress in the arm BC, and we have to show that where this maximum torsional stress and bending stress are located, or they will or act. Okay. As you can see, the cross section of arm BC is a rectangular. So if I draw a rectangular here, so this is the rectangular. We have to I have to demonstrate what type of moments or torque are acting on this cross section. As you can see, this load F is in distance with arm BC equal to, if I'm not mistaken, 38 millimeter. So there is a torque here acting on this cross section, right? That equals to 1.3 kilonewton, 1.3 kilonewton times the distance, which is 33 millimeter, I will convert it to the meter. Okay, so as you can see, the torque will be 49.4 Newton meter. Also, due to the presence of this load and this distance from the axis of x, we will have moment that will deflect or deform the RMBC in this way, right? Due to the presence of this load, we will have a moment which will bend RMBC in this way. And this moment equals to F times to this distance, which is 100 millimeter. So 1.3 kilonewton times 100 millimeter, and the moment is 130 Newton meter. So we have this torque and moment. Now we have to calculate the shear stress which causes due to the presence of this torque here and the bending, or sorry, the axial stress due to the bending. Okay, let's use our textbook to find some equation. If we refer to section 312, which is torsion, right? You can see equation 340 is about the torsion of a rectangular cross section. The maximum shear stress in rectangular BC section bar occurs in the middle of the longest side B, and its magnitude can be found by using this equation. That means the longest side here is B and the shortest is C. Okay, so I will write down the equation here. Equation 340, right, in which B is the dimension of longest side and C dimension of shortest side. Okay, so I will substitute torque B, C. You can find the value of B and C here in the shortest side is 6 millimeter and longest is 30 millimeter. So 0.03 and 0.006. So you can find that the maximum shear stress is 153 megapascal. The location of this maximum shear stress due to the torsion is at the middle of this longest side. So here is the value, here is the location of maximum shear stress, here and here. Always maximum value are important for us. Okay, as I mentioned earlier, the RBC will bend due to this load and moment of 130 Newton meter. To find the axial stress due to the moment, we have to use this equation, in which m is the value of the moment, c is the distance of the desired location to the neutral axis of the cross section. To find the second moment of area I, we can refer to textbook appendix table A18. For rectangular cross section, second moment of area can be found by this equation. And later on again we need this table to find second polar moment of area J. Okay, so as I told you, the rectangular cross section, the second moment of area can be found by this equation. And C is the desired location from the neutral axis. For the rectangular cross section, the neutral axis will be located at the center of the cross section. Since we are looking for maximum, stress or axial stress, that means it shows that maximum stress will happen at the maximum distance, right? That means the bending stress will be maximized at the outer location of the cross section. That means at the center we have bending stress equal to 0, and here we have maximum tension, and here we have maximum compression stress. In these two locations, at the maximum distance, we have maximum tension and compression stress. Depends on the type of bending, the direction of moment, and one side we have maximum of tension, and another side we have maximum of compression. So at the middle, at the neutral axis, the stress equals to 0. Okay, so this maximum distance equals to h over 2. So I will substitute h over 2 here. Then this can be cancelled by this, and this can be cancelled by this. So we will simplify the equation by 6m divided by bh2 for square for rectangular cross section, and then we will substitute 130 the moment of arm BC, and d is the width of the cross section, and as I told you, h is the height of the cross section, which is 30 millimeters. So the maximum axial stress due to the bending is 140 megapascal. So as you saw, the maximum torsion happens here, or located at middle of here, and maximum bending is here. There is another shear stress due to the bending. Actually, in the problem, you are not required to find that, because it asks you to find only the maximum of torsional stress and bending stress. It didn't ask you to find the shear stress due to the bending stress, but you can find that at chapter 3, section section 311, shear stress for beam in bending. Okay, If you refer to table 3.2, we can see the distribution of shear stress due to the bending. Unlike axial stress, I mentioned that beam under bending, always maximum axial stress at this location here. Maximum shear stress maximum axial stress were here, these two locations. But unlike that, the maximum shear stress due to the torsion will be happen at the neutral axis. So if I draw the neutral axis, you can see that the maximum shear stress will be happen at the neutral axis of cross section. In similar way, if the circle cross section, the maximum shear stress will be located at the center of the cross section. The value of this maximum shear stress can be found for each geometry by using this equation. For rectangular, a tube, a circle, and a beam. In these equations, V is the shear force and A is the cross-section area of the cross-section. Okay, so the maximum shear stress due to the bending can be found by using this equation. After we find this, okay, this is the maximum shear stress by bending, right? So earlier we found the maximum shear stress due to the torsion. And as you can see, these two maximum shear stress, both they are located at this location. Now we can either add or subscribe these two values to find the resultant shear stress at this location. But how to determine whether we have to add or minus these two values? In order to realize that or differentiate that, we need to draw a stress element here. We were looking for this cross section. Okay, so due to this torsion, if we, let's say, we look at from this point of view, okay, if we look at this point of view, the torsion is counterclockwise direction. So the torque from this point of view, the torque will be counterclockwise direction, and as I mentioned earlier, the maximum torsional shear stress is in this location, plus the shear stress due to the bending. Okay, if I choose a stress element at this location, right, and I draw the stress element, somehow that this face is at your front view. That means when you look at this point of view, this face, you can see this face of the cube. That means this is x direction. So due to the bending, we will have this axial stress. We call that sigma x. And because the torque is in this direction, so the torsional shear stress tau xy will be in this direction. And as you know, the first subscript x shows the normal axis of the face, and y, the second subscript, shows the direction which is in y direction. Also, due to the bending load F, or normally we call that V, the bending load, because bending load is in y direction, also the shear stress due to the bending will be tau xy. So at this location, these two shear stress, which they are tau xy, one of them by bending, another one tau xy by torsion, they are both in the same direction. So we will conclude to find the maximum shear stress at this location. Since they are in the same direction, we can write that maximum shear stress at this location is tau xy of the bending plus tau xy of torsion. Okay, I haven't found this value yet. Okay, 3 times V, which is 1.3 kilonewton, divided by the 2 times area of the cross section. Okay, so the result is 10.83 megapascal. Okay, 10.83 megapascal plus the shear stress to the torsion is 153.68. Okay, so the total is 164.47 megapascal. This is the total shear stress at this location of beam BC cross section. So we found this resultant or total shear max uh, as something extra work because it didn't require to find that in part B. You were only required to find the maximum torsional shear stress and the bending stress, which is that here is sigma x, and this is tau xy due to the torsion. Okay. In part C, we have to locate the stress element on the top surface of the shaft at A and calculate all the stress components that act upon this element. Okay. Locate the stress element on top of the surface. That means if I draw the support and the shaft, I have draw the stress element at here at the top and call that A. Okay, now I have to find first that what type of moment and torque will be applied to this point. Okay, due to the presence of load F, the shaft AB will be bent in this way, right? Shaft AB will bend in this way. And this moment is load F times 125 millimeter. F times distance, which is 125 millimeter. Okay. And due to the presence of this torque, sorry, this load, we will have a torque which tends to rotate or twist the shaft AB around its own axis or around axis X. And this torque is F times 100. So T is F times 100. But later on we have to convert them to meter. Okay, so 100.3 kilonewton times 100 millimeter, then we will have 130 newton meter, and the moment uh, is F times 125 plus this distance, because I neglect the first this part, so let me correct it. 125 F times 125 plus this distance, which is 38. Okay, 1.3 times 125 plus 38 is over moment at location A. Okay, if we look at the cross section, which is a circle, due to the presence of the torque, let's say that we are looking from this point of view, the torque will be clockwise. Okay, so due to this clockwise torque, we will have torsional shear stress, and as you know, always torsional shear stress is 0 at the center of the cross geometry and will exit to the maximum value at the outer surface. So the distribution of torsional shear stress is in this way. Here we have 0, here we have maximum shear stress. Okay, so in all the points
And
at
around the
the
circle or circumference of the circle, all these points we will have maximum torsional shear stress. And as I drew earlier, the distribution of axial stress or tension by moment or bending moment, the distribution will be in this way. So again, at the center, sigma x is 0, and here we have maximum axial stress. So here could be positive and here could be negative tension and compression. Okay, since this beam will be bent in this way, so at the top of shaft, that means point A, at this top we will have positive axial stress because it's in tension, right? And here we will have negative axial stress because it is in compression at this point or at the bottom of the shaft, top and bottom. Okay, to find the maximum axial stress or axial stress in x direction, because the shaft axis is in x direction, again I have to use this equation. To find the second moment area of the circle cross section, I can refer to table of that I showed you earlier, A18. Table A18. Right? Okay, second moment area for circle cross section equals to pi d power 40 over 46. And again, in order to find the maximum axial stress, I have to consider the maximum distance from the neutral axis. The neutral axis again is located at the center of the cross section. So if we say that the diameter is d, the maximum distance from center to, for example, here is d over 2. Okay, so we will substitute d over 2 instead of c, and this will be cancelled by this and 32. So the equation can be simplified in this way: 32m divided by pi d power 3. Okay, so now I can substitute moment, which is 211.9 Newton meter here, and the diameter of the shaft. So let's see how much was the diameter of the shaft. It is 20 millimeter. That means 0.02 meter. And therefore, the axial stress is 269.94 megapascal. Alright, to find the torsional shear stress for this cross section, we can use this equation, TCJ, in which J is second polar moment of area. J is second polar moment of area, and again you can find
equation in this table. P power 4 divided by 32. Again, we will write here and it can be simplified in this way. So here, uh, actually this is T. Okay, so the torque we found 130. Substitute here 130 times 16 divided by pi d power 3. So again, here is the maximum, sorry, yeah, the maximum torsional shear stress is 82.8 megapascal. If you want to indicate the direction of this uh, torsional shear stress, again you can draw a, let's say that we draw a, sorry, we draw a stress element in 3D way or as a cube, right? That means uh, this is a stress element at location A, and we are looking through this point of view, the front view. So this is the face that we are looking at the location here, right? So therefore here we have sigma x, and to find out uh, the direction of the torsional shear stress, since the I think that I drew somewhere. Okay, since the torque is in this direction or clockwise, therefore we can say that the torsional shear stress will be in this direction. So we call that tau x z, right? So I can correct this tau x z. Okay. Again, I will repeat one more time. I have choose a stress element at location A. I draw a Q to indicate this stress element, and therefore from this front point of view, uh, this is a direction of axial bending stress sigma x, and since the torque is clockwise, so shear stress at point A is tau x y. Okay. In the next part of this tutorial, for example, we are required to determine the maximum normal and shear stress at point A. Okay, since axial stress and shear stress are in different plane, I have to use more circle to find out the maximum to find out the principal stresses. Okay, so let's say, okay, we want to find the maximum principal stress or normal and shear stress. So we can use more circle equation. Okay, and here we can actually modify this equation based on our needs. So if
Since
we
we had
since we have sigma x and tau x z, so we can actually modify this Morse equation as we need. For example, we can say sigma x, sigma z, and therefore here we have sigma x, sigma z, and tau x, z. Okay, so uh, if I go back here I had only sigma x and sigma z is 0. We didn't have any stress in z direction, and we had tau xz, so I can substitute into Morse-Sigel equation sigma x 269 megapascal plus again sigma s minus sigma z, which was 0, divided by 2 square plus tau xz that we found is 82.8, and we can find the principal S, which is 293. Also, if you put a minus here, right, and a minus here, then you can find another principal stress. That we will have two principal stress. And also you can find the maximum shear stress at this location again by using this equation, but we can modify in over for over stresses, and again sigma x plus tau x z. So maximum principal shear stress is 158. Let's say that someone asked me to find the maximum stresses at location B somewhere here. If someone asked me to find maximum stress at location B here, in this location, since it is at the center of the cross section, or it is located at the neutral axis of the cross section, this point B, definitely here sigma x is 0. Okay, so at this point we don't have any axial stress, but at the same time we will have again tau. Let's say we are looking from here, it will be tau x y. Here we will have tau x y. The direction of the shear stress will be like this, tau x y. If we draw an element, let me draw from beginning. Okay, if I draw the stress element for this location, as I told you, sigma x is 0, so I doesn't need to draw, right? And there will be a torsional shear stress in y direction. So this is tau x y, and this is x direction, right? Like this, x y z. And also we will have the shear stress due to the bending. The shear stress due to the bending, which distribution is this way. Here we have the maximum shear stress due to the bending, which will be minimized at the top and bottom of the surface. So again here we have maximum shear stress due to the bending. And how we can find this maximum shear stress due to the bending? We can refer to our textbook at section, shear stress for beam in bending table, this table.
table 3.2, we can find that shear stress due to the bending is 4V over 3A. So let me write here T max due to the bending is 4V over 3A. Again, 4 times 1.3 times, because it's kilonewton, and 3, the cross section of the diameter is pi r, or we can write in this way 0.02 square over 4. So we can find this maximum shear stress of the bending, and later on, since these two shear stress are in the same direction, we have to add them to find the maximum shear stress at this location. Okay, so we have to again add the maximum shear stress of bending and maximum shear stress of torsion to find the maximum shear stress at location B. And as I mentioned, the axial stress or sigma x at this location is 0. Okay, I think we had completed the task of solving this example, and I hope that it could be useful for you. Thank you very much.